we will discuss about hyperfine interactions. Before this, we discussed actually fine structure or fine structure interactions, in which we derived expressions for spin orbit interaction and relativistic corrections. These both contribute to the fine structure interactions, the fine structure corrections, and these were a sort of perturbation in the case of atomic structure and in the case of atomic spectra. If you remember that these interactions were of the order of some 10 raised power minus 3 magnitude. The only magnitude above these interactions is what about 10 raised power minus 3, that is alpha is approximately 10 raised power minus 3 with units, fine structure constant. These are some of the magnitudes, and it is too large as compared to the hyperfine interactions. Because hyperfine interaction is a sort of perturbation. Like we have fine structure, we have hyperfine interactions, or fine interactions which include spin orbit interactions and relativistic interactions. So what is the origin of these hyperfine interactions? We will discuss in brief. And if you remember that the radii of nuclei is of the order of minus 4 angstrom, which is 10 raised power minus 14 meter. And this radii of nuclei, it is very small as compared to size of, so not size, actually it's a distance, as compared to distance of electron from nucleus, and that distance is approximately 1 angstrom. This is 10 raised power minus 4 angstrom, and this is 1 angstrom. So obviously 1 angstrom is much larger than 10 raised power minus 4 angstrom. Why I am telling you, you will know it in a very soon. Nuclei are very heavier as compared to electrons, orbital electrons, that is extranuclear part, and that is about 10 to the power 4 times heavier than electrons. So using these two concepts, that means this distance is very large as compared to the radii of the nucleus. The mass of the nucleus is very large as compared to the mass of the electrons. So there is a finite distance, which is approximately 1 angstrom, and this distance is 10 raised power minus, this is 10 raised power minus 4 angstrom. This distance, radii, it is not diameter, it's only radii. This. So the radii this, and the mass of this nuclei, it is very much heavier as compared to these electrons here of any orbit. This leads to a good approximation, a very good approximation. We can say that from these two conclusions that nuclei to be positive point charges of infinite mass. That means, assuming these two properties of the nuclei and the electrons, we assume that the nuclei is of infinite mass with positive charges. And this has been used up to now. We have used this approximation up to now. However, this is just an approximation, and this has given some better results when we assume this approximation. This has given some better results when there have been experiments because when an object is moving or object is located at a far away distance from the observer. I have studied in classical mechanics as well. When the distances are large as compared to the size of the object becomes as a point, is treated as a point object. That is why we treat nucleus, because its size is small as compared to the distance between the electron and the nucleus. The size of the nucleus is very small as compared to its distance from the electron. That means at electron that becomes an observer. So when you observe at the position of an electron, you will see that this nucleus seems to be like a point object. That's why we treat it as a point object, a point charge. Since it has positive charges, so it becomes point charge. So there is some charge which is concentrated in this region. So we treat this object as a point object. But this was one of the things which led to the fine structure constant and as well as all those. But very high, very precise experiments or highly precise experiments, high precision experiments reveal that existence of tiny effects on the electronic energy levels. That means that if we assume that it is too far away from the electron, and we are assuming that it is too heavy at this position as compared to the electron, when we assume those two properties, we can say that since it is not affecting any electron, it is not affecting the electron energies because it is too far away. And if there is any field which is because of the nucleus, that field at such large distances will not interact with the electron energies. When it does not interact with that electron energies, there will be no extra effect on the electronic energy levels. So I'm repeating that when we assume that this object nucleus is of heavier mass and it does not move, one point. Another point is that it is far away from the electron. So these two properties can result in saying that any effect or any field which happens to be originating from the nucleus, which has the origin as nucleus, like nuclear magnetic dipole moment. This is one of the electromagnetic field. So that field in these approximations, under these approximations, does not affect at all the electronic energy levels, because we are assuming that it's too far away. we're assuming that is not moving from its position, it is infinitely heavy. This is an approximation on the basis of which various results have been derived. But when very highly precise experiments have been done, when in atomic physics, like there's a Fabry-Perot interferometer, very sharp, those what are those called, slits actually, and if you are using a monochromatic laser light, so those laser lights have very sharp those width, or they can interact at very minute levels, at microscopic level, at atomic level. These, when the experiments are done with these type of sources, it has been revealed that there is a effect, there is a change in the electronic energy levels, and that change actually arises because of the field of the nucleus. Now, so that means this was just an approximation here, but this approximation does not remain valid when very high precise experiments are done and there are seen that there is some shift in the electronic energy levels, apart from the fine structure, that is spin orbit, relativistic, and also there is a lamp shift. Lamp shift is also on the, it gives rise to the fine structure. So lamp shift actually is an assignment for you. I am evaluating your earlier assignment as well. Last one, Pauli acceleration principle and electronic configuration. So lamp shift is another interaction between the, there's an electromagnetic field and of electromagnetic field and the electrons. So that affects the energy levels of the electron, but that becomes an perturbation. Similarly, in this case, when there are the fields which are arising from the nucleus, because of the nucleus, then there are the hyperfine interactions. Based on the magnitude of these interactions, these are very small as compared to the fine structure perturbations. Another one is that this is one effect. So this is one thing. So hyperfine interactions, these result in two things. So one way is that it can split energy levels, electronic energy levels. So the effect of the perturbation, which is because of the hyperfine interactions, can result in the splitting of the energy levels of the electron energies. That means a splitting of electronic energy levels. One way. Another thing is that what can be assumed theoretically without incorporating hyperfine interaction. That means if we are not incorporating any hyperfine interaction and calculating the position of the electron energy, that means electronic energy levels, without this interaction, and then we incorporate the hyperfine interaction, or there is a change in the mass of the nucleus. There is a change in the mass of the nucleus, then there is a shift of electron energy levels. So there are two effects which can result because of the variation in the properties of a nucleus, like the charge or the size, mass. So there are two properties, charge and the mass. Charge, there's a magnetic dipole moment then. So that magnetic dipole moment and the mass of the nucleus has two different effects on the electronic energy levels. Those two effects are either it can split the electronic energy levels more than two components, two or more than two components, or it can shift the energy levels when we vary the mass of the nucleus. If you see this This is simply called as hyperfine effect. Simple, in simple terms, the definition is. And when you go talk of this shifting of, sorry, wait. So yeah, splitting is hyperfine structure effects, and the shifting it arises because of, it is called as isotope effect. It arises because of isotope effect. So isotopes, you knew that masses are different. So when you vary the mass, when you change the mass or replace the atom by its isotope, there is a shift in the energy levels of the electrons. Though it is very small, of the order of 1 centimeter inverse, it's very small. I will give you an example and we will derive it. We'll see how much this comes out. This this equal to isotope effect. That means shifting of the energy levels. When it arises, it is because of the isotope effect. And when there is a splitting, that is because of hyperfine. When there is isotope effect, there is shifting without splitting. This has been observed. Shifting, there can be shifting without splitting. This is slight shift, but there is a shift which can be measured. And when it is splitting, that becomes hyperfine structure effect. When it is shifting, that becomes isotope effect. For example, I will give you an example. Sorry. You know that when we studied the hydrogen spectra, and if you know that this 1 by lambda h, which is equal to nu bar centimeter inverse for a hydrogen atom, it is equal to RH divided by N1 square so you all know this we have already done. And in addition to this, if you remember RH, what is RH?
Rydberg constant.
It is Rydberg constant. So do you know the expression for it? And if you remember this, we have derived it for the case of reduced mass. There we have used reduced mass approximation. So this mass actually enters directly to the Rydberg constant. It is directly involved in the Rydberg constant. Mass of the atom, mass of the nucleus. For infinitely heavy nucleus. And then it becomes, for infinitely heavy nucleus, it becomes Me4 divided by 8 epsilon naught square H cube C. It is this. Okay. And if you take it for a normal simple nuclear mass, Rm, where m is the mass of the nucleus, this Rm is less than R infinity for infinitely heavy nuclear mass by factor of 1 over 1 plus m by m. It means that this Rydberg constant for any nucleus or an atom having mass this m is different because their involve was this m. We have derived this expression actually, I have shown you. So it is different for the atoms of different masses, Rydberg constant. And that spectral series you derive actually, or you observe it by using that concept of Rydberg constant. Okay, now in case of hydrogen, this isotope shift is seen more prominent. It is more this the variation in Rydberg constant is particularly marked in hydrogen. The variation in Rydberg constant is particularly in hydrogen atom. For example, each of the 4 members of Balmer series, that is H alpha, H beta, H gamma, and H delta. These are the 4 components or 4 members of the Balmer series. First 4, they have a very weak component. That means there is a very weak spectral feature. If it is a line spectra, there will be an observed slight faint line, weak line on the short wavelength side. That means high energy. And if we plot it on the new centimeter inverse, and this is H alpha, here is H beta, H gamma, H delta, then somebody is writing on the screen. There's a, and this is new centimeter inverse in the units of new centimeter inverse, and this is the higher energy side. This, so on the higher energy side, there's a very weak component here along each of these series, each of these components here, very weak components. And this appears at from this point. Who is writing? Somebody is writing. Please remove these arrows.
Weak component.
New, it is wave number. It is not the frequency. 1 by lambda. Actually, it is new bar.
Yes, sir. Sir, आपने बोला weak component.
Weak component. Weak component. Weak component. That means its intensity is very weak. By weak, I mean the intensity is very weak. Okay?
Okay, sir.
So if you have any question, you can tell it here. You can say it here. So what is your confusion?
सर फिर सीरीज लिमिट जो होता है वो
Series limit is something different. Series limit is some when you approach, when you consider the transition from the very large value of the energy level. That means n equal to 5 to n equal to 2. Like it is, what is how we denote the this, what is called Balmer series. So we represent it 1 by h equal to nu bar. It is RH for hydrogen atom. It is 1 by 2 square minus 1 by, for example, this is the first line of the Balmer series. H beta line. This is for H beta.
Yes, sir.
Okay, so when you go on increasing the number of higher energy from which the atom relaxes into its ground state. These lines.
Yes,
so
sir.
when you go towards this n tends to infinity, that is series limit. When transition comes from this level to ground level, this n equal to 2.
Yes, sir.
Okay, so this is for h equal to h beta line, this component, and these weak components in case of these for h alpha and h beta, there's a distance of 1.33 centimeter inverse. Angstrom, sorry, not inverse. So this is actually in angstrom, it means it's a wavelength shift. Short wavelength. So it is a wavelength. It is in terms of wavelength when I write an angstrom. So if you want to convert it in nu bar, you will divide 1 by 1.33. That will give you nu bar. Centimeter inverse. Okay. So this is the shorter wavelength, high energy region, high wave number region. But this is lower wavelength. Sorry, yeah, high wavelength, lower energy region, because they are opposite in nature. So there is a distance, apparent gap between the series and these weak components. For H beta line, this is H beta, it is 1.33. Here for this H alpha, it is 1.79 angstrom gap between. For this case, it is 1.19 angstrom. For this case, it is 1.12 angstrom. So this is the separation between the hyperfine components and those spectral lines, from which appears from the Bohr's theory of hydrogen spectroscopy. If you want to now see that what is the effect of isotopes on this spectra, that means what will happen to the hyperfine interactions or the energy levels of the electron when we incorporate the perturbation due to the change in the mass of the nucleus, that is the isotope, change in the isotope. Now 1 by lambda h is equal to RH 1 by 2 square 1 by 4 square. This is for H beta line. Okay, and you all know that there is a component of hydrogen 1 2. What is this? Deuterium. Okay, because this is also called as heavy hydrogen. Who is drawing these arrows? Somebody there, you might remove it. If you have any issue, please write a message or talk here. Heavy hydrogen. So heavy hydrogen was actually discovered in this by the method of spectroscopy itself. So this is the case for hydrogen beta line when we talk of hydrogen 1 1. When we have a presence of deuterium, which is hydrogen 1 2, then it is observed that there is a change in the Rydberg constant, which is for the case of deuterium or D, and it is 1 by 2 square for the case of deuterium. And remember that H beta line has a wavelength 4861.33 angstrom. This is the wavelength. Now, if you take the ratio of these, it will be simply equal to RH by RD from these two expressions. This and this. Okay, RH by RD. Or I can write it as lambda D minus lambda H Is it okay? So it gives us delta lambda, which is equal to lambda D minus lambda H, sorry, is equal to minus lambda H.
सर
Just
आवाज नहीं आ रही है
rearrange the terms. I have rearranged the terms only. This is delta lambda. This lambda H goes to here, and take this minus common, it becomes RD minus RH. So it is minus lambda h. This is the wavelength for the Balmer series of the hydrogen atom, H alpha, H beta line of the Balmer series. So it is minus, we can write 4861.33 angstrom into, if you incorporate the mass of this deuterium into the Rydberg constant, it comes out the centimeter inverse minus okay. See here, these are different actually. Rydberg constant becomes different by changing the mass, and it becomes 1.32 angstrom. Okay, so you can see that the change in the wavelength, the shift, this is the shift actually from deuterium to hydrogen. When you replace hydrogen by deuterium, there will be shift in the electronic energy level. That is the H beta line of the deuterium. It will be at this position. This will be the gap between these two, difference actually. Okay, so this is how the difference arises because of the isotope effects. So this is the simplest case for the hydrogen atom, but it is not always easy like for rare earths. And heavier atoms. The contribution to main contribution to isotope effects in case of these rare earths are the heavier atoms, because hydrogen is a lighter atom with one electron for hydrogen, and deuterium it has 2 protons. So in that case, for these cases, these arise actually, these isotope effects. So there is not only the variation of the mass in the isotopes. When you increase the number of nuclear charges, there is a variation in radius of the nucleus as well. That is size of the nucleus. So because of isotopes, you can have either from the mass, that is only the isotope number of charges, or the mass of the nucleus, or you can have effect because of the radius of that nucleus due to the increased number of the charges. Okay, so this is how actually the isotope effects contribute to the hyperfine structures in the hydrogen in any spectra, in case of in the spectra of the atoms. Now another one is which I already discussed with you, is that this was an isotope effect. Now there is hyperfine structure effects. These are the structure effects. That means hyperfine effect is there, but just because of the structure. And structure means that the structure of the nucleus, because of its that shape, the different shape, there is a but definite angular momentum, the magnetic dipole moment, for which L is not equal to 0. That dipole moment of the nucleus interacts with the dipole moment of the electrons, and you know that electrons has orbital as well as the spin dipole moment. So when it is interaction between the nuclear magnetic dipole moment with the spin, it acts as a perturbation. In the same way, when there is an interaction of the magnetic dipole moment with the orbital dipole moment of the electron, then that acts as a perturbation. So we have these two perturbations, or we have to simply see the effect of these two interactions on the energy levels of the electrons. So hyperfine structure effects are those effects actually which arise due to the interaction between the internal magnetic field produced by the orbital motion of the electrons in the atom and the spin magnetic dipole moment of that nucleus. There is a magnetic dipole moment of the nucleus, and this interaction, the effect of this interaction, give rise to the hyperfine interactions, structure effects, or the components which are called hyperfine components in the spectra. And these are very small in magnitude, so the effects are small, and the intensity of the components is very weak, and they have been observed experimentally by very highly precise experiments. In those cases where these have been detected, the light sources, which I already told you that there must be one which give extremely sharp lines without any finite width. Those sources must be one which will give us extremely sharp lines. Like there's a lamp which is called a Schuller lamp actually. We can use laser sources. We can use interference spectroscopy. We can use by like Fabry-Perot interferometry. So these are different types of those sources which we can use. These are also called as, which are because of the magnetic in nature, magnetic origin in nature, also called as magnetic dipole hyperfine structure. The hyperfine interactions, because of this magnetic movement of the nucleus, these are also termed as magnetic dipole hyperfine structure. And it was a Wolfgang Pauli in 1924 who suggested that nucleus has a total angular momentum I, which is called as nuclear spin. So hyperfine structure effects actually, hyperfine structure effects, these are the hyperfine structure effects. These arise due to magnetic interactions between the nucleus and the moving electrons of the atom. Depending upon this important orientation of this nuclear spin. So the magnitude of the effects will determine by the orientation of the nuclear spin.
सर ये पॉइंट फिर से रिपीट कीजिए.
This. So hyperfine structure effects, these arise due to the magnetic interaction between the nucleus, because nucleus has a spin here, magnetic moment, and the moving electrons of the atom. And this interaction will be determined by the orientation of the nucleus spin, net spin total. actually the magnitude of that interaction. Because it is just like you keep an magnetic moment in the external magnetic field. We already studied the magnetic dipole in external magnetic field. So treat the electron as a magnetic dipole and treat the nuclear magnetic moment as an external magnetic field. So we already know that if you keep a magnetic dipole in an external magnetic field, it will try to align it its own direction. So if this is B in that case, and you have that spin here, it will try to align. If it is close towards this direction, it will be easily moved. The magnitude will be large. Instead of, if this spin is in some here direction, it needs a lot of energy to be oriented along the same direction. So these, using this concept of Pauli, that there is a nuclear spin magnetic moment, and this spin magnetic moment will interact with the orbital and the spin magnetic moment of the electron, then we can explain the hyperfine structure effects, or hyperfine correction to the atomic spectra. So we can write that the magnitude of spin or nuclear magnetic moment, it can be written as, this is I not Z, H cut, and this I is spin quantum number of the nuclei, and it is different. This I is a spin quantum number which has different values for nuclei of odd mass number. You all know this from the nucleus, those shared model and all that. So angular momentum has different magnitudes for different nuclei and also for different isotopes of the same element. Because when there is a change in the isotope, there is a change in number of nucleons. There is a change in number of that spin. Then that results in the net angular momentum change. If you apply some external field in the z direction, then as z will be equal to mi h cut. Just this is an analogs to that electronic system, electronic magnetic moment. And you also know that this mi should be equal to I minus 1, I minus 2, up to minus I minus 1, and it will reach to minus I finally, minus I minus 1 actually. Minus, there is I throw 0 to minus I, or minus I throw 0 to plus I, like it is minus L throw 0 to plus L. There's also, we know that there's a motion of that nuclear protons actually, that the magnetic moment, let that magnetic moment be denoted by mu I. There's a nucleons. It is proportional to the angular momentum actually, and we can write it as, it is Gi Is it okay up to here? I think it is S here in case of electrons, or spin angular momentum. Similarly for L. So these both are for the charge of the mass, charge and mass of the proton. This, yeah, I can write here simply MP, mass of the proton, and here Gi is nuclear G factor. If you want to find the value of this mu I, it is Gi E by 2m into 2mp under root of using this value for this. This is subscript to m, this p, and EH by 4 pi mp. It is nuclear magneton, like we have Bohr magneton. EH by 4 pi m, simple. And if you calculate the ratio of mu I over this mu n over mu b, if you calculate the ratio of this, it is m by mp, which can be written as m by, which gives us that mu n will be equal to m by mp into mu b. Also, this mu n is 1 by 1836 times mu b. That is because, why it is so? Because mp is 1836 times me, mass of electron. These are just the facts about the nuclear, this electron and proton. We consider a hydrogenic atom with nuclear charge Ze and its magnetic dipole moment mu I. For this system, if you want to write a Hamiltonian H for an atom, where there is a contribution from the nuclear magnetic moment, interaction between the nuclear magnetic moment and the electronic magnetic moment, or the magnetic moment of the electron, so H can be written as H0 plus H dash or HMD dash. This is just a notation for this. Then this H0 is actually a zero order Hamiltonian, unperturbed Hamiltonian. It includes Coulomb interaction, that is minus Z E square divided by 4 pi epsilon naught R, and the relativistic, which we have already done, fine structure corrections, as we already discussed, relativistic plus spin orbit and all that. This is all included in this. Now those terms become unperturbed. These are already there. While this perturbed part, it is a perturbative here term, and it arises due to the presence of magnetic dipole moment mu I then our aim is to find this. In calculating this, we will see that this term is very small than this fine structure term or any other terms, because the magnetic moment of this nucleus is smaller than that of the electron. We already know that if I can write here, I will write here, let me see. Yes. The Schrödinger equation, or the Hamiltonian of an atom in electromagnetic field, radiation, simple radiation, electromagnetic field of the nucleus, which is time dependent, is minus h cut square by 2m del square minus ze square 4 pi epsilon naught r minus I h cut e I h cut e divided by m a dot del. Just remember, rewind that electrodynamics, plus e square by m 2m into a square. Do you remember this expression? Especially these two terms. What is a? Anybody?
Coulomb gauge.
So A is a vector potential which satisfies actually the Coulomb gauge. And this AR in the electromagnetic field is given by dipole moment and if you have it done, I recommend you to do it. Because del of 1 by r is equal to r magnitude divided by r cube. From simple this vector calculus, the first unit of the Griffith. So this is up to you. You have to do it, and you have to also find if h dash is equal to minus I h cut e by m a dot del, then find a dot del, or find h dash simply. H dash equal to, by using a here, and you can use that, of course, mu I, that is g m I mu n, that you can use here. So I will see this tomorrow and we will continue from here tomorrow.